Yeah. So thank you very much for the invitation. And okay, so I'm glad to be here, and I'm happy that I can present you this little course, which is made of 6 lectures. The idea is that what we want to do is to classify universality classes. Universality classes are a fundamental topic in theoretical physics, because basically they are equivalent to the classification of universality classes is basically equivalent to a classification of possible conformal field theories. And the universality, sorry a moment, wait a second, let me put this full screen, okay. Okay, that's now. So, first of all, I assume a little bit of background in renormalization group. So I assume you know what is a beta function. I assume you know what is a conformal field theory. And I assume you know what is universality. And I assume also that you know quantum field theory, okay? So what we're going to do now in this course is to find the first way. So our main goal is, and is the main goal of the G analysis, is the classification of universality classes in arbitrary dimension. Why are universality classes important? For many reasons. First of all, because they classify the possible phase transition that a system can undergo. This is the infrared physics of universality. But at the same time, there is the universality UV aspect to universality, and universal theories are needed to construct a continuum limit. Okay, and so in general, asymptotic freedom and asymptotic safety. Universal quantities are quantities that can be measured and that they are independent of the microscopic details of the system. So actually, this is one of the type of quantities that we can measure in experiment, and we also, from an epistemological point of view, understand why some quantities that we compute, they can be observed in nature. For example, why is the solution of the two-dimensional Ising model so important? It's not because there is really a microscopic system that behaves like the next to neighbor interaction of the Ising model. What is important is that the Ising model is a representative of the universality class. And so, it's a simple system that we can solve mathematically that behaves at the critical point, at the phase transition, exactly like a real system, which is much more complicated. So universality has, first of all, this epistemological value, because it's really one of the reasons why our models were able to predict nature. But at the same time, and this was the great unification that was made by Wilson, that he unified the infrared and the ultraviolet, we need to make sense of a quantum field theory. To solve the problem of renormalization in a definitive, non-perturbative way, we need ultraviolet fixed point with a specific structure. One example is when the ultraviolet fixed point with a specific structure is the Gaussian fixed point, and for example, this is underlying the continuum limit of gauge theories, but also the fixed point can be non-trivial. In this case, we speak about asymptotic safety. The third reason is that in most cases, and in particular when we are speaking about equilibrium statistical mechanics, equilibrium quantum field theories, okay, Euclidean quantum field theories, in that case, it's almost granted that a theory which is a scale invariant, so a fixed point of the normalization group, is also a conformal field theory. So basically, every conformal field theory can be seen as a fixed point of the normalization group. Vice versa is not true in general out of equilibrium. It's not true when there is not unique, in some cases when we are at equilibrium. So at the same time, the ability of charting all possible universality classes is like a first map of all possible conformal field theories. And so our goal is really the one of making an atlas of universality classes. How many universality classes can be present in a certain dimension with a certain number of degrees of freedom? In the course, we will focus more in scalar degrees of freedom. But it's also true that many times a universality class can have a representation in terms of scalars or in terms of fermions. And the example is always the two-dimensional Ising model that can be represented in the continuum as, you know, as Majorana fermions, or as a non-local, fully interacting scalar field theory that we cannot really write in closed form, but we can only represent in an approximate way through the renormalization group. So the goal is really to make a map, and in particular to make a map of universality when there is a multi-component case, okay? When the order parameter has more components. So to do this, we, in the recent years, there has been quite an activity in this direction. And in particular, there was the insight that if we work at the functional level, and not just at the level of the couplings, and now this will be the main topic, a lot of things become more clear and more simple. In particular, we realized that if you want to write down beta functions and study universality classes, the renormalization group flow of scalar theories with multi-components, you do not need to make new computation every time, because the beta functionals of the multi-component scalar field theories are actually deducible from the one component scalar field theory beta functionals. Also, the beta functional have a structure that can be obtained, as we will do today, without even having to do a loop computation. And so at the end, because the functional constraint is much more stronger. And at the same time, the beta functionals are the generating functions of the beta functions. So it's like in many situations, if you work with the generating functions, you make life much easier than working directly with the quantities that you're trying to compute. Then there is another byproduct of the analysis, is that in this way we learn that we can access with the Epsilon-Expansion also some OPE coefficients of the conformal data, not only the critical exponents. And again, this is possible because we do not need to make new computation every time, as we will see. And from the other side, the Epsilon-Expansion is the top side. If you think about universality classes, they will leave, for example, the Ising universality class becomes non-trivial below 4 dimension, and it goes all the way down to 2 dimension, where it's a specific conformal field theory. So if you think about conformal field theories as, okay, we know all of that, we know a lot of things in 2 dimension, where you have studied conformal field theory, you know that the Virasoro algebra allows you the full classification and construction of what is called the minimal unitary models that have a finite number of fields and a lot of very interesting properties and can be solved analytically. Okay, this is the bottom line. And then each one of this universality class, basically is it present in every dimension all the way up to the upper critical dimension. And so every integer dimension in between 2 and the upper critical dimension is a place where you have the candidate. You will have this conformal field theory, which will need some non-perturbative method to be constructed, to be used to compute these properties. And in particular, there are 2 of these strong methods. One is the non-perturbative version of DFG, and the other one is the conformal bootstrap. And in fact, we had many collaboration also with people in that community of the bootstrap, because once you want to go beyond just the Ising model and want to study more systematically the universality classes to treat with the bootstrap, you need to know which theories you expect, because it takes you a lot of time to construct the formalism and to do computations. So the Epsilon-Expansion, which is clearly the original method, but in this revised version allows us to map all possible universality classes and know in each dimension where to find which universality classes you can expect, and you may want to construct with non-perturbative techniques. Also, another thing that came out from this analysis is that, first of all, you will see that once you want to treat universality classes in the Epsilon-Expansion, you will discover that as the level of the one component, DC, which is the upper critical dimension, is basically a label of the universality classes. But not universality classes in perturbation theory have the property of the Ising model, that they manifest themselves at one loop and have the next to leading contribution at 2 loop. Normally, other universality classes manifest themselves for the first time at a higher loop order. And for example, we found out that there was a universality class that manifests its presence for the first time at 3 loops, but has upper critical dimension which is bigger than 3. So together with 6 and 4 is another upper critical dimension that can be used to create non-trivial universality classes in 3 dimensions. Okay? So the lesson is that most universality classes have a fractional dimension, and their leading order is bigger than 1. So it means that when we do dimensional regularization, we need to look at, 3 loops, and we need to look at poles in the gamma functions in some fractional dimension. So the first thing we're going to do today is to answer the question, which are all the possible critical dimensions? So we're going to start from the higher level and try to construct a general picture of universality classes. And then we are going to, staying at this general level, we are going to construct the beta functionals. And only really at the last moment we will do some loop computation, because we realized that most of the coefficients can be fixed without even doing the loop computation. And then next week, we realized the biggest bonus of the functional approach is that when we go from one component to n components, we do not need to do any new calculation. So this means that in every textbooks that you normally study, when you do the OM model, you do again loops. There is no new loop to be done, because actually in perturbation theory, the group theory part and the RG part completely factors away. And there are very few coefficients which are the universal data that once you know them, and the goal of today and tomorrow is to construct this atlas of universality classes, which will be a big table where we list all the fundamental information from which you can construct any RG flow in perturbation theory without additional computation, but just working on the group theory part, on the understanding how to construct invariants, projecting them out, and studying the fixed points. Let me try again. So please ask questions if there is something that you need. Let's see. Yeah, what is we're going to define what is a universality class. So a universality class is basically, so here we are going to use it for the moment. Let's say, okay, a universality class is a fixed point of normalization group together with the Bayesian of attraction. So this is the standard definition. At the same time, by universality class, I speak about the fixed point. So it's a scale invariant theory or it's a conformal theory. It's a little bit interchangeable at the moment. And in particular, yeah. So this is the.
So it doesn't mean universality usually means that you can. It carries over to various different kinds of theories. But this is just every different form of field theory is a different universality class.
No, is that so? Yeah. So okay. We know that I'm giving for granted the knowledge of what is a universality class, what is the RG. So we know that we can construct models in many different ways. For example, this Ising model, we can construct it as a spin system. We can construct it as a conformal theory. We can construct it as a Landau-Ginzburg-Lagrangian. Okay, and we have a system. We know that for what matters criticality, most of the details are washed away. Okay, and so all theories, and these theories can be of all different formalisms. They all belong to have the same infrared limit. So what happens then is that one way to label universality class is to relate each universality class with its upper critical dimension. So for example, when I have one component and the upper critical dimension is 4, this is the Ising universality class. Because when I construct the Epsilon-Expansion, compute the RG quantities around this point, I am resolving that theory. For example, if I want to construct the tricritical model, which is the second one in the family of the multicritical model in 2D, I have to take upper critical dimension 3. If I want to construct the third minimal model, I have to go to upper critical dimension 8/3. So in the one component language, each universality classes for me is labeled by its upper critical dimension. And it's a fixed point which lives in between the upper critical dimension and 2, where it normally maps to a specific conformal field theory. So it means that now the critical properties that we can compute here, they are the critical properties of any model. So we will not construct explicitly the Bayesian of attraction. We only focus on the critical region and on the scaling region around it.
So different CFTs are different from their studies.
Yes, exactly, for sure. Different CFT. So you can just say CFT if you just go to equilibrium and so on. We want to classify possible CFTs which can be represented with scalar components as a Landau-Ginzburg-Lagrangian. Okay. So the question is, how many are there, especially when we go to multi-components, and in which integer dimension we expect them to exist? Okay. So we are going to work with a very simple traditional action for a scalar theory. This week we are going to work only with one component. Okay, so we have it's an Euclidean scalar theory, in a d dimension to be specified. And actually this is the key point, because the key point of all the construction is that depending around which dimension I am expanding, which will be the upper critical dimension of a given theory, I am actually constructing the critical point of a specific conformal field theory. Then, as we have learned in quantum field theory, we have that we construct the effective action. Okay, so we have this is like a fluctuation. So much space. Times e to the so this is the definition of the effective action, which is the generating function of 1 pi diagrams. It's the way in which normally we see the conformal quantum field theory. It's a functional that comes from the integration of all the degrees of freedoms. Okay, so it's basically the quantum action, and the quantum action has a loop expansion. By applying the saddle point expansion here, you should know this formula very well, which is normally is also graphic. We write it like at so we have that the tree level is the action, and then we have 1/2 the trace log of the Hessian, and then we have this is the one loop diagram, and then we have a 2 loops, this contribution, and then we have this 2 loop diagrams and so on. Okay, so this is the standard framework of perturbative quantum field theory. Okay, we're gonna put some exercise about it if you want. And then, as you know, when we do this, there is the problem of divergences. You know that these diagrams are divergent. Okay, so you need to regularize them. And in particular, of the many types of regularization, the one which is most common, most useful in perturbation theory is what is called dimensional regularization. So these diagrams, which are a certain integrals, 2 loop integrals, 2 loop diagrams or 2 loop integrals. So 2 loops or 2 integrals, 1 loop is 1 integral and so on. You need to regularize them, and in play, how do you regularize them? You work in a dimension which is a complex dimension in general, in the complex plane, but you analytically continue D. So if you're studying your theory in D critical in certain ways, you just go around that. We will see one of the key things you have to bring home from this week is that actually DC labels universality classes, because once you choose a specific DC and you study criticality, you are basically studying that universality class or this other universality class. And then we need to actually work with the renormalized loop expansion. Okay, so we need to add counter terms, all the classical things that you have learned in the quantum theory course. Okay, I give them for granted, even though what I'm going to teach you is that we can avoid most of these details if our interest is computing RG, beta function, and criticality. We're going to go actually around. We just know they exist, but we are going to use only the general properties of it. Yes?
So, when you say DC labels in universality class, you mean a universality class composed of theories that near criticality look like that?
Yes. So basically, yeah, perfect. Thank you. So basically, it means that every universality class has an upper critical dimension, which is the dimension above which the fluctuations become Gaussian. Okay. Now, for each type of each universality class has a different upper critical dimension. So it means that when you do perturbation theory around that specific dimension, and you're in one single, you are actually studying that particular theory. So if you want to study the tricritical model, you have to work in D critical 3. There is no sense you work in D critical 4. Because when you compute property in the Epsilon-Expansion in D critical 4, you're actually studying the Ising model. Everything that you compute, fixed point, critical exponent, and so on, they pertain to that theory. Okay. So in fact, what we're going to do now is ask the question, which are the possible DC? And this actually gives us a table of the possible universality classes. And then we will infer the structure of the beta functionals. And then we will go to multi-component. So in this way, we're going to take a top-down approach. Okay. Now, this is an example of some diagrams, you know, the loop expansion. These are the gamma 2. So here I'm using the so the effective action has, you know, the 3 level, then it has the one loop diagram, which is the trace log, and then it has, so this is gamma 1, this is if you want, and if you want you can put an H bar here, then there is a gamma 2 plus H3 gamma 3, and so on. Each one of these, as you know, they can be drawn as diagrams, and since we are working in the loop for the effective action, diagrams are closed diagrams. They are evaluated we are working in the background field. So in principle, these things have to be evaluated in the background field. So for example, when we look at this diagram here, as we were looking at before, okay, which is this one. So you see that here we have, this is an S3, this is another S3, and these are the propagators which are equal to the inverse of the Hessian. Okay? So when you compose this, these are actually implicit integration over A, B, C, and so on. Okay? And then you can normally evaluate them in momentum space. Even though we will almost not evaluate diagrams, but we will be interested in their topology, because most of the conclusions come out from that. Well, it's the first exercise of the course. So this is the gamma 2, okay? And what is important in these specific coefficients are very important because they are the mother of all the symmetry factor of loop diagrams, of Feynman diagrams. Because once you want to compute an amplitude, for example, you know, gamma is the generating function of one PI diagram, so you will act with external legs, and the combinatorics will generate all the symmetry factors of your diagrams. So these are the master formula of perturbation theory. Everything in perturbation theory is descends from this formula. So it's important to have a little bit of knowledge of them, how to work them out. And in particular, okay, gamma 2 is known. Here I display also gamma 3, and as an exercise you should be able to write down the diagrams and the coefficients, okay? Because you should be able to enumerate them. What we're going to see today is that most of this will not be needed, but it's nice because we're going to use it as a reference. So here, for those who want to get a diploma at the end, some of the exercises you should do. So this is, if you do not know how to do this, you should learn how to do it, because it's a little bit systematic. Okay, it's a core of the thing. So this is called the loop expansion for the effective action. Okay. Okay. Now we introduce the main player of our lectures, which are the beta functionals. Okay. So you probably know what are the beta functions. Okay. We know the beta function of the coupling lambda phi to the 4. You know. And we know that the beta function of lambda is equal to 3 lambda square over 4 pi square. You have done this in Pesky-Schroeder in any quantum field theory course. Okay? So these are beta functions because they pertain just to the coupling. So when we specify the potential to have a specific form. What I'm going to show you is that if we are just a little bit more general, like it happens a lot of times in mathematics, we just see the overall structure. We actually gain a simplification and a better understanding. So we work with the beta functionals. Keep in mind that the beta functionals are the generating function of the beta function. So it's like they are generating functions. As you know, many times generating functions simplify your life. Then we will obtain all the beta functions as coefficients of the Taylor expansion of these things, which are the beta functional. And in particular, we're going to focus on the beta functional of the effective potential, which is called beta V. And then we will also have the beta functional of the wave functional normalization. So now that we do the loop expansion is poisoned by divergences. Divergences will be regularized in dimensional regularization. And in particular, 1 over epsilon poles correspond to, if we instead work with the regulator, to terms which are log lambda. So they are dimension-less contributions. And since beta functions are of a coupling lambda is the derivative, if you want, of, so let's okay, is the derivative with respect to lambda of the coupling, okay? These derivatives, this is basically saying that we're looking at log lambda terms. As you know, as we will not review, 1 over epsilon poles, the coefficient of the 1 over epsilon pole defines the beta function, okay? I assume you know this part because we don't have time to review it. It is not. So what is really important is that at every loop order, okay, when I evaluate my diagrams, there will be divergences. Divergences in general, in dimensional regularization, if I'm looking at L loop order, divergences will go from 1 over epsilon to 1 over epsilon at the L. But it's only the 1 over epsilon part that the coefficients of which are called the beta function. And in particular, we take away a minus sign, a factor 1 over L for the loop order. And so at every loop order, there is a factor of this term. And the coefficient of the volume, okay, is what we call the beta functional contribution at that loop order. The coefficient of the cinetic term is the beta functional contribution of the loop order L for the Z. Once I examine my theory at various loop order, the full beta functional is the sum over the various loop order of these contributions. Okay? So these are our main focus, because these quantities encode all the beta function, all the critical exponent, a lot of information about the OPE coefficient, the existence or non-existence of fixed points. And so they are the RG quantities that we want to focus and that we want to construct. Okay? And this applies to any critical theory. So somehow this is the universal data. Also, in this series of lecture, and normally as we do in dimensional regularization, we are going to focus on the relevant and marginal sector of the theory, in the sense that there is even mixing with operators which are irrelevant at the very fixed point that will contribute other terms here, and they will also contribute other terms inside this object that we will discard, because we are going to focus. One of the key things about dimensional regularization is that the marginal and the relevant sector completely decouple from the other one. Okay, so we can really focus in a consistent way only there. This means that we want this object here to be constructed only of derivatives of the potential, and derivative of the potential that will have an order in the derivative that will not be bigger than the power of the marginal coupling. We will see this in a moment. So this is one thing. And then also what is really important is that for most universality classes, which means all apart the one that we know, the Ising universality class and the Ligand universality class, and notice that I will always use this typewriter letter to identify, most of them, the leading order contribution doesn't come at one loop, but will come at some order, which could be high. This means that most of the RG information is actually hidden in the loop expansion at various orders. Okay? And we will learn how to compute it. Okay, so now we pose the first question. The question is, okay, since I want to know all universality classes, I know that every universality class has an upper critical dimension. And normally, if this is like d equal 2, maybe, I don't know, this is d equal 3, and then this is the Ising universality class, where the critical is equal to 4. Okay? So this universality class exists in this range. Okay? And in particular, here is Gaussian, here is non-trivial, and is the universality class which we focus so much attention, and here is a particular CFT to D CFT, okay, which we know how to solve exactly. But now, okay, now we know that the Ising has DC equal 4 because we are so used about this that normally when we do quantum physics, we think that the only upper critical dimension is 4, and we think that we should do everything around 4, and we think that 4 is special because we live in 4 dimension. No, it's not that. Actually, the question is which are all the possible DC, because once we catalog all the possible DC, we have basically found all the possible universality classes that we can construct. So how to choose a DC? So which one is the plausible upper critical dimension? Well, an upper critical dimension is one that will give us some non-trivial beta functionals, okay? Some non-trivial RG information. So the question is, in which dimension can we find loop diagrams to have 1 over epsilon pole? Okay? So that's the question. So when the background field is taken constant, okay, because this is gamma, we take this is constant, and so it means that all the derivative terms drop out, okay? So we are looking only at the terms that will contribute to the beta function of the potential. So now, once we have a diagram, so now we need to figure out which are all the possible upper critical dimensions. So take a diagram like this one, okay? This is, so what does this diagram in perturbation theory is basically, we have one integration here, another integration because we have two loops. Then below we have 1, 2, 3, we have a certain number of propagators. So this will be to the number of propagators, okay? Then it can also happen that we look at diagrams with the mass insertion, with the V2, because the full propagator is Q squared plus V2, okay? Where the field is constant. So this thing here, we will expand it as 1 over Q squared plus 1 over Q squared V second 1 over Q squared. So in general, something like this will have here this plus K, where K is the number of mass insertions, okay? So we see that this thing here will have a 1 over epsilon pole when we'll have divergences which are proportional to logs of the cutoff, okay? So this happens when the powers of momenta up in the numerator are equal to powers of momenta in the denominator. Okay, so in this case, we are going to write, this is the loop order. Okay, so when we have dc times L is equal to 2 times P plus 2 times K. Okay, so this is the condition that we generally have. K is the number of insertions, so K can go from 0, 1, 2, and so on. So we can write that the critical is equal to 2 P plus K divided L. So now, so here, this runs over the integers plus the naturals. So what is the value of P? P cannot be 0, but at a certain loop order, there is a minimum value, which is equal to L plus 1, okay, when we are above one loop. So P minimal is equal to 1 if L is equal to 1, otherwise if L is bigger than 1, okay? Because here we are, okay, because for example, in this diagram, where L is 2, you see that the number of propagator is 1, 2, and 3. This is the one that has the highest number here. So if we insert this inside here, we're going to have 2 times, and then we have L plus 1 plus K divided by L. And so this one we can write it as 2 plus K prime divided by 2 times K prime. And now K prime goes from 1 to infinity, but we can consider that it goes again from 0 because it's basically the L equal 1 case. And so this is the family of all the possible upper critical dimensions. Okay? And then if we work out instead L in function of dc, we get this formula. And this is basically showing us which is the loop order. So if I fix dc and I go with k over the naturals, the first time this quantity is going to be an integer is the leading order of this upper critical dimension. So the first time, then a diagram will have a 1 over epsilon pole. Okay, so this is to say that. So let me see.
Can you remind the definition of critical dimension?
Yes, the critical dimension is a dimension where the diagram has a 1 over epsilon pole.
Okay.
Okay.
The mean of K.
Huh?
The mean of K.
K.
Yes. What is it?
K is the number of insertion of mass insertions.
Okay.
Because In general, this is, so with our, remember our action is the genetic term, so plus this. So our action has this simple propagator. We're looking at the vacuum bubbles with constant external field, so the propagator is just this is an effective mass. So then if we just ask ourselves when it's this thing having a log, it's diverging like a logarithm, it's when the numerator is equal to the numerator. And so this happens when this is here. And then we just want to express the term in terms, eliminate P by saying that, okay, in any case, if we're looking at DC, we're looking at the first time that, the first diagram of that family that will have a divergent term. So for example, let me, you can make, so how to use this formula, we are just saying that, okay, for L equal 1, so K can be equal to 0, so K equal to 2. Only for L equal 1, K can be equal to 0, as we said. So we're going to make a table like this. And then here we're going to do like L equal 2. And then we're going to do L equal 3. So for example, if we take our formula, so DC is equal to 2 plus 2K over L. Okay? So K equals 0 is allowed only in the one loop case. So in the one loop case, this goes from 0, 1, 2, 3, 4. So these are just these numbers here and so on. A 2 loop, we have 2 here. This goes away. And so K goes from 1. So we have 3, 4, 5, 6, and so on. And then if we go to 4 loops, 3 loops, we have 2 over 3. So we have the first time some rational numbers, and these are the rational numbers that we have, and so on. We will have, in a moment, we will see that we have to impose another condition on the possible upper critical dimension, which is the one that we will have to stop with Landau-Ginzburg-Lagrangian that have at most 6, because starting from 8 upper critical dimension, the Landau-Ginzburg-Lagrangian will be fractional. A fractional power. There will be another constraint. In any case, so this is the logic to get this table, which is the first table of our lecture today, which answers the question, which are the possible upper critical dimensions, okay? So we see that at one loop order, we have only 3 possibilities, which is 4, 6, and 2. At 2 loop order, we have some novelty, 3 and 5. At 3 loops, we have 8 over 3, 10 over 3, and so on. And you see that when a universality, an upper critical dimension is born, it will stay with the period of its original loop order. So for example, 4 will have a period of 1, will be present at every order, like 6. But 3, for example, is born at 2 loops, so the next contribution will be at 4, and the next leading will be at 6, okay? And so on like this. So this is the post answer to the question, which are the places where we expect loop diagrams to have 1 over epsilon pole, which means where the beta functionals are non-trivial. There is some beta functional. If there is a beta functional, there is that will be an upper critical dimension with a well-defined RG. We have taken away this other part of the table because the corresponding Landau-Ginzburg action. Okay, now this will correspond. Now we have to do another thing. We have first of all to ask which one is the marginal coupling, the marginal operator in that dimension, okay? And to do that, we just need to remember that what is the dimension of the field? Basically, this one. You know, what is the dimension of my field? It's K2 something. How do I know that? I know that the measure has dimension K to the minus DC. I know that this term here has dimension K to the DC because it's the cinetic term. So this one becomes this one squared times this one squared. This one is just K squared. And so this is these two, let's call delta phi, no? So this is 2 times delta phi. This has to be equal to k. This is k to this is k to the dc. And so we get that delta phi is equal to dc minus 1. Okay? I am neglecting for the moment the anomalous dimension in this thing. So this is the dimension of the field. Okay? So the question is, which one is the marginal coupling or the marginal interaction? So I have to look at the term like this, okay, and I want that this thing here has, again, the is equal to k to the dc, because I want my action to be 1/2 squared plus lambda phi to the n, okay? So I want this one to be dimensionless, k to the 0. And so from this thing here, I find that n is equal to 2 dc over dc minus 2, okay? So clearly, this is the operator which is marginal, so the one that in the Epsilon-Expansion will be the non-zero coupling at the fixed point. So this is the Landau-Ginzburg-Lagrangian that correspond. I want this thing here to belong to the naturals, okay? Positive naturals, because we do not know how to make sense of a irrational field theory where this thing is not an integer. Actually, following this line, you can construct the RG of these theories, and they are very sensible, but we do not know how to construct them in other ways. So we will impose this condition. And imposing this condition is basically cleaning up a lot of entries in the table. And clearly we end up that each upper critical dimension, which is allowable, it's related to a Landau-Ginzburg-Lagrangian with an integer power. Okay? And so this is something, okay, we made a long route to something that could have been obvious in a sense, but it's important because what is important of this table is that it makes us clear that, first of all, only these 3 universality classes have an upper or appear at one loop. And if I want to look for a specific one, I have to go inside the loop expansion and specifically look at there. And then the contribution, this will be the leading order contribution, and then I will find next to leading order contribution. And in particular, there is this theory here, the Fudge the fifth, that has upper critical dimension, which is 10/3, which is bigger than 3. So this is another upper critical dimension that may have or has a non-trivial fixed point in 3 dimensions. And actually, this was overlooked for a lot of time until we were the first ones to describe it. And the main reason is that you have to look at 3 loops to find the first non-trivial information. Okay. So in any case, since we were working at the one component, we realized that, okay, all the forms of our Landau-Ginzburg-Lagrangian are of this type. And they are like the multi-critical models. And they actually divide into families, the one which are even models and the one which are odd models. So the even model are the most famous family in quantum field theory and conformal field theory, because they are the one who are becoming minimal models which are unitary in 2 dimensions. And the first one of the family is the Ising model, the second one is the tricritical Ising model, and so on. While the other family, the family which is odd, has the first in the family is the Ligand universality class. And they are non-unitary. This means that the coupling is basically imaginary, but they make perfectly sense as statistical mechanics models. They don't make sense as fundamental theories, but they are interesting and they describe a lot of interesting physics. So we know from Zamologic in particular that the unitary family goes to this particular set of multi-critical models in 2D, but we actually know only where the first one of the other family goes, thanks to Cardi, had made a famous paper on that. So in particular, the picture that is emerging for us is this one. So remember, we started with the question of which are the possible upper critical dimensions where diagrams have divergences, and they were all this one. And then we posed the condition that the Landau-Ginzburg-Lagrangian should be integer, and they just become the blue and the red family. Okay, and now I will just redraw this picture, but focusing on, so in particular, if this is 2-dimension and this is 3-dimension and this is 4-dimension and this is 5-dimension and this is 6-dimension. So we have one theory, which is the Ligand universality class, that is present in all these integer dimensions, okay? And in particular, in 2 dimensions, it becomes the minimal model 2,5, the one pointed out by Cardi. So this is a very interesting universality class because it's actually in this set of order parameter is the only one which is non-trivial in 4 dimensions. Okay? And so if it is non-trivial in 4 dimensions, it can also have some application in principle in high energy physics, if we can find a way to make it unitary. Actually, this can happen when we look at more components of the field. Because now remember that we're working with one component, but then when we grow with a number of components, this will still be the upper critical dimensions for which we will study, but each one of these will become should explode in a variety of different universality classes that can host a lot of different symmetries. Okay? Then we have the second one. The second useful upper critical dimension is 4, and this is Ising. Okay? And Ising, as we know very well, it is very interesting in 4 dimensions, in 3 dimensions. And this is the multi-critical model. Here I write, this is the loop. The leading order loop is 1. The leading order loop is 1.
So it's 5 to the 4, right?
Huh?
It is in 2 dimensions. It would be the first one would be 5 to Q, in 6 dimensions.
So sorry, can you repeat?
Now let's look at the left one.
Yes.
So in 6 dimensions it would be 5 cube, right?
Yes. This is all phi cube. Yes.
How do I think of it in 5 dimensions? What happens in 5 dimensions?
It's like when how do you think about the Ising model exactly in 3
I
dimensions?
don't know. I'm not an expert. That's why I'm asking.
Okay. So you need a way to construct it non-perturbatively. So if you do the non-perturbative RG, you will follow this fixed point that starts from here all the way down to 5, and in 5 it will actually be represented by a lot of different invariants. If it is a conformal field theory, it is not even represented by a Lagrangian. But what we know is that for each one of these universality classes which has this kind of description around the upper critical dimension, they exist all the way down to the minima.
How do you know this?
Huh?
How do you know?
No, this is not a theorem, but it's something that we have observed. For the
What is evidence? Or
Huh?
what is
The evidence is that the non-perturbative methods allow you to construct this. For example, these two have been studied with non-perturbative methods, and so the fixed point in this case has been traced all over the dimension. For the case of the Ising model, it has been constructed between 4 and 2 with both the bootstrap or with the non-perturbative normalization group.
How can you have non-perturbative method in fractional dimension where the whole thing is only defined through fractional dimension?
No, but they are analytical continuations. But both the non-perturbative RG and the bootstrap can be made
Analytical continuations of what?
analytical continuation of your equation in function of the dimension in which they work.
But then how can you analytically continue from a discrete set?
No, this is not discrete. These are continuum field theory, so they are continuous constructions.
But it is only defined for integer dimension.
For integer dimension is only defined you mean the universality class or the
The theory is only defined for integer dimensions, and it is only defined by God.
No, this we are discussing here. So here we are only discussing perturbatively around the upper critical dimension. The upper critical dimension can be fractional. For example, we see now the next example is here. It's 10/3, and here you can construct a theory in rational dimension. You can write down the loop diagrams. You can look at the divergences, and you can find exactly like an integer dimension. They have the same status. But okay, what I want to represent in this picture is that these are the dimension where a candidate universality class with these properties is expected to exist. So here you can think, okay, I want to construct a theory with the same symmetry, which is zeta-2 symmetry and one order parameter in 3 dimensions, you can construct it with any method you have and you expect to find it. Okay? So what I'm trying to make here in this picture in particular is to have, clearly we know them from the upper critical dimension, we know them in 2 dimensions, and generally they exist in the other integer dimension where we can construct them. So this is a map of this type. Then we can speculate exactly what it means to have a theory defined on a fractal or these kind of things. But it is not really the main topic of what we want to discuss. The point is that perturbative theories can also be defined in fractional dimension. Fractional dimension, as we see. This one, for example, is called a tricritical Ligand. And we will see example. We will do the beta function. We complete the spectrum. We can construct it with a conformal field theory. We can construct it with the non-perturbative G, and there are various things. The point is that we have, and the point is that this one we do not know to what it goes. And then here we have other upper critical dimension, 8/3, and this is the 3. Sorry, then there is the upper critical dimension 3, okay, and this is the 3 critical. And then we go on, and then we have 8/3. We have the tetracritical and so on, okay? And this we know what they are because they are some specific minimal models in lower dimensions. This is 5/6, and so on. So the point is that we normally, in 2 dimension we can characterize this universality class as minimal models. Around the upper critical dimension, we can construct the universal quantities, which are critical exponent, these kind of things. The value they have at the point here is the main field value for that, and we can construct normally the first and second derivatives in a universal way using the Epsilon-Expansion. In the integer dimension where we expect them to exist, we need non-perturbative methods. Okay? For example, the non-perturbative G or the bootstrap, or like simulations. But this gives us a map, an idea where to find and what to find. Okay?
What is on the x-axis?
Nothing. This is just a way to represent them.
But what is in common between Ising and Untitled?
So,
what is this vertical line? This vertical line represents...
Yeah, this is what I want to say, that the Ising model has upper critical dimension 4. So you expect, and then these are the integer dimension that they enclose. So here you expect to see an untriggered theory. This is just a diagram, is not a plot of a quantity.
I don't understand what it means here, because I don't understand what's on the x-axis.
X-axis is just integer related to the
vertical axis is dimension, right?
Yes, this is the minimal model. It's just the theory. This is just a diagram. It's not like it doesn't have a. It's not a plot. Something. So you just say the first universality class, the second one, the third one, and so on. Okay. If you want, I can organize here. Okay. If you want, it's the power of the field. 5 to the 3, 5 to the 4, 5 to the 5.
Yeah, that's what I was trying to understand. But it doesn't make sense in lower dimension.
No, it makes sense. So all of them go down, and the point is that they will accumulate. So here you will find all powers, but most of the universality classes have an upper critical dimension which is below 3. So they are interesting only in 2 dimensions. Okay.
In 2 dimensions, can I visualize somehow the power of 5?
Yes.
How?
It's the same. So this minimal model here, okay, it's 5 to the 4. This is 5 to the 3. This is 5 to the 5. This is 5.
Minimal models are not Lagrangian.
Minimal model, so they are not Lagrangian, but Zamologico has shown that this one and this one, so the even one, can be represented by Lagrangian. And is this Lagrangian here?
In 2 dimensions.
In 2 dimensions. So basically, if you want, you are saying that the descendant of this field is, they are related in this way. You can impose on your conformative theory. And you can do this actually also. So
Yes.
okay. Wow, slide again. Okay, let's Let's go again.
Can you make some comment about the distinction between unitary and non-unitary cases?
Yes.
You said the 10/3 line, in 3 dimensions, you expect that to be a non-unitary.
Yeah, this one are unitary. The point is that, as we will see, their fixed point is going to be complex, imaginary. So
So it's a statistical model.
So it's a statistical model. It's wait a moment.
Is there a statistical system known whose exponents are?
Yes, this is the Lee-Yang edge singularity. How the zero of the partition function in the complex plane of the Ising model accumulate and behave.
Oh, that's for the.
Yeah, no, the other one. Yeah, the other one is a critical version of that.
Okay.
And it's basically that thing for the Bloom-Capell model in statistical mechanics. That's the reason why it's also referred as the Bloom-Capell universality class. Okay, so now the point is that now we have found this map, and we have understood where we have non-trivial RG information in the Epsilon-Expansion. Okay, we have in this dimension for these things. And apart, we learned the periodicity, the loop order, and so where to look inside. So now for each one of these, we expect, if we do the computation, to have a beta functional for the potential and one for the wave functional normalization. One of the most interesting things of this approach is that, well, we actually do not need to infer their form. We do not need to do the full computation and look, because we can just basically determine the functional form of the beta functionals once we know DC. Because we know that in dimensional regularization is a scheme that doesn't have a mass scale. So we just need to look at which are the possible contributions, which are dimensions to the beta functional. So the beta functional will be constructed out of monomials with the various powers of the vertices that they can compare, they can appear. The vertices that can appear, we can read them off from the knowledge of the diagrams, okay, that we pictured before. But at the same time, we can just obtain them from the basic topology of vacuum diagrams, okay, and dimensional analysis. So, for example, what we're going to do is that, okay, for each, the logic that we're going to follow. So now we're going to do a little algorithm, a little analysis that allows us to write the beta function of V. Once I define, for example, B critical equal to 4, will be equal to various contributions. This contribution will have the form of some monomials, okay, written out of the potential. And so to do that, we can do one thing, which is the first thing to do is, okay, I just need to look at the diagrams, okay? And I will know that if I'm looking at the contribution that comes from 3 loop diagrams, you can only have some particular type of vertices, okay? Each vertex here is a certain derivative of the potential. So for example, this is a V4, this is a V3, and so on. Wait, let me go here. Okay, so the logic I want to follow is this one. So first we construct something that we call the vertex set. So which are the possible candidate vertices, monomials, that can appear at a certain loop order. So for example, if we are at two loop order, we have 2 diagrams. Okay. So this diagram can furnish something like this to the beta functional. Okay. This diagram can furnish something like this to the beta functional. But we are working in dimensional regularization, and in dimensional regularization, one can show that bubble diagrams which are just a diagram of lesser order, for example, one loop with a bubble will not give a contribution. So only diagrams which are not lower order with a bubble will contribute. So at order L equal 2, this is the only building block of my beta functionals, okay? Clearly this thing here in a given dimension will have a certain dimensionality. And I need to construct something which is dimensionless. So I can multiply this thing here by powers of the mass insertion in such a way that the total dimensionality of this will match the upper critical dimension in which I'm working. And then this is the only candidate monomial I can have in my beta functions, okay? Now, this is a 2-loop. If I go to 3-loop, okay, if I go to 3-loop, I can look at...
So how did you find out that this material can be static with the potential to...
Okay, so let me show. So now the question is, I have the beta function here, for example, in a certain upper critical dimension. This can have contribution at 1 loop, at 2 loop, at 3 loop, because we know that, okay? Apart the 1 loop contribution, which is trivial and we wrote it down, let's focus in the first non-trivial contribution is the one from 2 loop. So at 2 loop, I know that there are 2 diagrams, okay? This thing here will contribute something to the second power of V3, and this will contribute V4, okay? In general, now I ask myself, I know which is the dimensionality of this object in D critical 4, and in particular, this is not dimensionless in D critical. So I need here to multiply by a power of the mass to a certain power k, and if I can find a k, which is an integer that satisfies that this thing is dimensionless, then here there could be a contribution of this form. Okay, so in particular will be this one, okay? If I am working in a general scheme, also this thing here can give me something proportional to V4, but now I will use the fact that in dimensional regularization, bubbles added to a diagram of lesser order, which is a 1-loop diagram, will not give a contribution. It's the same. We can also draw this contribution simply in dimensional regularization. Their coefficient will be 0. So then here I will have a coefficient. So the 1-loop, okay, just write this. So then the beta functional will be a number times these monomials, okay? So how, and the point is that I can write down these monomials just by using the basic topological formula, the Euler invariant for the diagrams, without actually needing to enumerate all possible diagrams, okay? Because, for example, if we go now to the example of a 3-loop, these are the possible building blocks of the beta functional. And there are 2 ways to get them. One way is to look here in these diagrams, okay, and see always the one with the highest degree will not contribute because it's a bubble, so we just take it away. But then we have something like this one, and if you see, this thing here is V3 to the power 4. So this is one possible building block. Then another possible building block is 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. So it's V3 square times V4. Then another possible building block. You see that this one and this one have the same building blocks. So the number of building blocks is much smaller than the number of the diagrams. That's the reason why we don't have to go through all of them. Then we have like V4 to the 4th power. But then you see that V4 to the 4th power is also presented in a diagram that will not make a contribution in dimensional regularization. And then in particular here there is also V5 times a V3. But in this case, this is just a bubble connected to another one. So we list it because we have to list it, but then when we compute the coefficient in dimensional regularization, it will be 0. So you see that by inspection of the diagram, I can get this set here of building blocks, okay? And then once I have this set of building blocks, I will just have to ask myself, okay, this is valid for, this is loop order 3, and now it's general for every upper critical dimension. Now I ask myself, in upper critical dimension 4, which of these monomial can I make dimensionless by adding a power of v second? If it is possible, this will be present in the beta functional. Okay, this is our logic. What I want to show you before writing down the result is that actually we can infer this thing which we call the building blocks, the vertex set, okay, simply by topology. Because we know that every graph must satisfy this equation. So there is a relation between the potential, the number of vertices and the power p of the propagators. And then we can ask ourselves, so over which values of p does it run? P runs, let's take p as, so L is given, let's choose p to be our dependent variable. So then p will run from p minimum to p max. So how do I achieve p minimum? P minimum is achieved by the sunset diagram. Okay, one like this. And so it is, I have one propagator more than the number of loops. I am already taken out these vacuum bubbles because they will not be contribution. So this is the P minimum. The P max is achieved when I have only diagrams with free vertices. Okay? So diagrams with free vertices I know that if I take a diagram and sum over all the vertices, the number of legs that come out from a diagram, this has to be equal to 2 times the number of propagators. Okay? So I take like something like this. So there are 2 vertices. If I sum, okay, I get 6, which is 2 times p. Okay? So if I have now that the number of legs I fix it equal to 3, I have 3v is equal to 2p. Okay, if 3v is equal to 2p and v is equal to p minus L minus 1, okay, so this happens for p max. I find that p max is equal to what I write there, which is 3 L minus 1, and v max is equal to 2 L minus 1, because it's, so it means that I will have, so the minimum contribution comes from the situation which is this one. So this will be v to the L plus 1 to the power square. While the max comes from, will be v3 to the power, which I write here, 2L minus 1. Okay? In the middle, what do I have? In the middle I have all the partition of 2p, because it's the number of places, of length v that runs in between p minimum and p max. Okay? So let me just make an example and then I show you a little mathematical code that does the enumeration of the contribution for us. So, for example, let's consider case L equal 3. So, P mean the smaller amount of propagators a 3-loop diagram can have is L plus 1, which is 4. So general diagram will have this. And the maximum is, as we said before, is equal to 3 times L plus 1. So it's 6. So it means that if I have P, this could be 4, 5, or 6. So 2P is equal to 8, 10, or 12. V, which comes from this formula, the Euler characteristic, is 2, 3, or 4. So now the building blocks, the vertex. So as I said here the building blocks are the partition of this number of length 2. So I can write this number as 4 plus 4 or as 5 plus 3. And they have 2 elements. Here I can write this number as 4 plus 3 plus 3. And here I can write this as 3 plus 3 plus 3 plus 3. Okay? So you see now that this thing here just gives us back these 4 elements, which are the same one that we got by looking at the diagrams. The point is that looking at the diagrams is a much more over constrained, it's much more general. We don't need to do that. We just need to run this little procedure, and we know which are the possible building blocks of the beta functional at the general loop order. For example, if you run this in 4D for L equal 4, you find that all the building blocks of beta functionals are of this form here. And let me show you one moment. I wrote here a small code. So here I write, for example, L equal 3. So can you read? Put it better, bigger. So here I just write L equal, for example, L equal 2. There is only the V3 square, no? L equal 3. I have these 4 cases. L equal 4. These are the cases which are listed in the slides. Okay. And you see here, I just write down this thing that this little topological argument, okay? So we have all the building blocks. Now that we have all the building blocks, the next step is the one of completing them according to the upper critical dimension. So this is now where the information of which universality class we are studying comes into the game. So now I will say, for example, so we remember that this object here has dimension, the dimension of the potential, which is D, and the dimension of n times the field. So it is the formula which is written there as D minus n, d alpha minus 1. N times the dimension of the field and then dimension of the potential. For example, okay, it's clear that the one term I don't use is only the V2 to this power. It's so trivial that I'm not explicitly. Let's look at the two-loop contribution. So we know that the building block is this one. Now we can add a vertex insertion. So now if D critical is equal 4, this quantity here has to be dimensionless. So if it is dimensionless, it means that I need to, this thing here has to be satisfied because it's 2 times the dimension of the vertex plus 2 times this is equal to D. DC. So let's see what it is. So D critical 4, so the field has dimension. So this thing here, let's go. So this thing here is, so it's 4 minus 3 that multiplies 2. This contribute. Okay, so just, and then we do the same. So this is for the 2 loop, and then for example, when we look at the 3 loop contributions, we have these various terms, and we just write down a linear equation. Okay. So then we have here the monomials. So it's this. So this is the dimension of the field of the V3 Vn. For example, we are working in upper critical dimension 4, and we look at the 2 loops. Okay, I run this, and it tells me that V3 can be completed to become dimensionless if I add this. Okay, so I discovered that if D critical is equal to 4, the beta functional has the form A, and this is the one loop term, which is obvious, but if you have doubt about that, we're gonna. But the first non-trivial term, which is the 3 loop, is the square of this times this one. Okay, and again, nothing else could be. So we have fixed. Then we can. So this is 1 loop. This is 2 loop, and then we can add. We're going to look at 3 loops. What is going to come out at 3 loops? 3 loops, I just go here and I just put 3. So at 3 loops, I can have, reading from here, let's say C1, and then I have, let me start from this one. V3 at the power 4 without mass insertion. Then I have another coefficient, and then I have V4 times V3 square V4 and then V2. Okay? And then I have another coefficient C3, and then I have I'm looking at V4 squared times B2 squared. And then I have plus B5, B3, B2.
So, sorry, this is beta function of what coupling? How do you define beta function?
Beta function we define at the beginning. At the beginning is the generating function of all the beta function.
What is beta function?
Beta function is the coefficient of the pole. It's the renormalization group beta function. It's the one that tells you how the coupling scale, the basing.
Which coupling?
Here we have all of them because the potential V will be the generating function of all of them.
What is usually people say that only the lowest order of the lowest non-dimensional order of beta functions are defined?
Yeah, we will see it so for example, all the beta functions that we do in quantum field theory can be deduced by this. Now we are working at a little bit more abstract level where we can do this general analysis. Then Friday and then Giovedì, the 2 lectures, we're gonna go all the way to the beta function, the critical exponent, all the traditional stuff. So for the lambda, here we are calculating. So this is the leading order contribution to the beta function of phi to the 4, the thing that we compute in every textbook.
Do I understand?
Huh? Yeah, we'll come to this one. This one is much more general. We generate all the one that you can compute in quantum field theory are coming down from this. Actually,
what is its physical meaning? What does it
no, the physical meaning is the same. This is the beta function, so it's the running of the couplings.
Running of what couplings?
The coupling of your critical theory. Every theory will have marginal couplings, relevant couplings, and even irrelevant couplings, and so on.
So in this particular example, what would it be?
Yeah, and these are the generating functions of the beta function. So first we obtain them, and then we come to this. This is like an output of our analysis that we do not tomorrow, the day after, where we connect to what you know. So, and theory like phi to the 4. So we have 1/2. So this is the standard theory for you have n squared and 2 n squared plus you can put it up in here, which is to the 3 plus. Okay, so this will have a beta function for m squared, a beta function for g, a beta function for lambda equal to something, no? All these beta functions will have a leading order, an leading order. They will all be generated by this scheme. But this scheme is more general because it allows us to, first of all, just do the minimal computation. Because you don't need to do an independent computation every time. Actually, you only need in the whole theory to know these 2 numbers. But now we are computing all the beta function of all the couplings for all the universality classes in one row, in one thing, apart coefficients that then we will fix by the simplest calculation that allows us.
Some mathematical technique or does it have some physical meaning?
No, it has physical meaning, like it has physical meaning for this one. This is the beta functionals, because normally it is the whole potential which is running, not just the coupling. You know, when you have a potential like this, only in some situation you can actually look at the potential running, normally it's the full potential. For example, if you want that the potential becomes completely convex in the infrared, like you expect from the potential, you need to look at the full running, not only the Taylor expansion. But then we can use the Taylor expansion of this to reproduce the beta function. But then this we can use also in an approach which is not based on the Taylor expansion. But for the moment, what I want to say is that I want to show that the beta functions for any theory, first of all, I want to have an approach that I can put all of them, not only the one of the easy model, and then I want to make it in the most efficient way, and then I want to make it in a way where I can generalize to n component without having to do new computation. So what I'm really doing is to compute all beta functions for all couplings for any component that have this hypercritical dimension now. This is what we're going to see. So it's this reformulation, which is a little bit more abstract, kills by a factor of 10 or even 50 the number of computation to obtain the true beta function. Next week we're going to work with a huge number of beta functions, but we will not have to write diagrams anymore. Actually, we only need this information from the diagrams to write the beta function. Okay. Yes.
This one thing
Huh?
Which you have emitted.
Yes.
In beta does not.
Hmm?
The beta.
Exactly. The reason we made this exactly to be dimensionless.
But how does this first term survive if it's it seems to be that it have that dimension?
Did I write something? Yes. The critical over 2. No, but this is dimensionless. Okay, it is dimensionless. These are the dimension. No, okay, this is. Let me see. Okay, in a moment I will come to that. Okay, so let me finish this thing, then I explain you what I understand your question. Okay, so now we can do this, and the outcome of this analysis is that we have come. Now you can run this one for each one of our upper critical dimension and for each one of our loop orders. Okay, so we know, for example, that the Ising model gets contribution to every loop order. So what we did here with this thing is that to understand that the beta functional of the Ising model, okay, has this form. Has a one loop term, okay, has the two loop term which we calculated was this one, has 3 contributions to the 3 loop terms, because we are going to drop this one, because this one is something that goes into the irrelevant part. Because the phi, this is something that gives a non-zero result when you put inside phi to the 5th power.
So the beta function is not really a function, it's a vector field on the space of couplings. So your expression is very schematic.
No,
Vector field has a form, like G d over dg plus blah blah blah.
No, but this depends on the background field. So this is.
Still, it's beta function, is not a function.
No, this is a beta functional. It's not the beta function. This is the connection between the two is this one. Beta of v is equal to a sum n equal to 0 or what you want. Here we write lambda n, okay, phi to the n. So the beta function of n. So this is the beta function of your coupling. It's a dv of lambda n. So this thing here depends on the background field, another constant, which is the background field that we use over there. So this is the beta function, but we are computing, by computing this object, we are computing all the beta function.
So I mean, it would be more constructive perhaps to write something like our semantic equation instead of this.
Yeah, but
just to see where you substitute this beta function. Beta function by itself does not have much.
Yeah, this computes the beta functions. This is we are computing the beta function. But the beta function have a meaning inside the Alessandro equation, inside the RG flow, and all that kind of things.
Okay.
The Alessandro equation is a equation that tells you how the vertices of the gamma are, but betas are unknown. Now we are asking our question: what is the form of beta? Well, you can compute them, but it is better for us if we compute the generating function, because the generating function we can do this topological analysis and dimensional analysis and write down, after we have understood all upper critical dimension, all the form of the beta function, nulls. Okay? And so these are all the contributions. And now, so you see that we can do this for each one of these orders. So in particular, let me stress, the new interesting thing is that, okay, this is how it looks, the beta functional of this theory that has upper critical dimension 10 over 3. Or for example, look at this theory, which is the tricritical theory. It has the leading order at 2 loops, and it has the next to leading order, which has this form at 4 loops. Okay? So we can carry over this, and up to here we didn't do any computation. Actually, we just needed the general properties of the loop expansion. We didn't need to compute all the draw all the diagrams. Even if you want this an exercise, try for the 4 case, draw the diagrams and convince yourself that the list that comes out from this little algorithm is complete. Okay?
So far, based on this is just the graph counting based on the 1 pi.
Yes.
Right?
Exactly. This is only the only thing you need.
So I'm trying to understand.
This is something I could have done without any formulas, but if I just go with the 1 pair effective action, then I can write down what terms are going to.
Yeah, this is exactly what we did. We just did
Okay.
which are the terms. So I just did that. I just wrote down the dimension. We did the dimensionless terms that can belong to BV. But to do that, you need to know the critical, because the critical, and you can do, if you look at the 1PI diagram, it means you draw all the diagrams. But what I'm just saying that with this one line of Mathematica, you simply don't need to look at all diagrams. You just need to keep this little relation that we did here. And in this way, you just write a code and it gives you out the form of all beta functionals, okay? And so you realize that everything comes apart, the coefficients, which are now the things that we need to know. So one fundamental thing is that only the leading order and the next leading order coefficients are scheme independent. So they actually need to be computed, because all the other one, the higher order one, can be changed by a change of scheme, okay? And then the key point is that now I can use the simplest situation I can imagine to compute the coefficient, which may not be. And once I have this coefficient, all the beta functions, all the critical exponent, all the OPE coefficients will come out as a product, because these are the generating functions of the beta functions. So I just generate all the scheme. And what is even more important, when we go to the multi-component case, we just need to add indices, and A and B will not change. So for example, for the Ising model, when I go to the multi-component, it will be the same form, because there is only one way to make this expression multi-component. And so A and B will not be needed to be, we don't need to recompute A and B. So it means that if you want to study the ON model in 4 dimensions, you only actually need to look at the free theory and the cubic theory in the singular component case to compute A and B once and for all. And once you have computed this coefficient for all the upper critical dimensions, you don't need to do any more RG computations. You just do to look at the group theory part that tells you how to write invariants for general structure. Okay, so that's the logic. And we realize that there are also other contributions, that other theories that we were bypassing before. For example, like this one.
Why are some of these things written in gray, or is it?
Yeah, no, this is in gray because this I am putting them in gray because this theory is a cubic theory. So this term here has a fourth derivative. So this is something that comes from the irrelevant sector. And now we are focusing only on the relevant part. You can clearly keep all the contribution for the irrelevant sector, but then you will also have contribution from the Z here. You can work them out exactly in the same way, but it's normally not the focus on what we're looking. So this is just to say that actually these terms are present, but they will drop out. So if you want, these are all the possible dimensionless terms. If you work with an arbitrary massive scheme, then these are some terms of the beta function. But now if you work with dimensional regularization, okay, some of them die because of this fact that they are bubbles. And if you look at the marginal and relevant sector, some of other one die, and so that's the resulting final set is smaller. Okay? Okay, we can do something similar exactly for the beta function of the Z. Okay? Exactly the same kind of reasoning, and write down the thing. And now we come to and so once we do this, now we are ready to summarize everything. And this is the summary that we were looking for. So this is our atlas of universality classes in the n equal 1 case. Okay? So what is the logic of this table? The logic of this table is that we set a certain maximum loop order, and we know that at this loop order, some universality classes appear. Okay? Because we know that at 3 loops is the birthplace of the. At 3 loops, we have the first contribution to the tetracritical universality class. At 2 loops, we have the first one of the 3 critical. The Ising and the Ligand have contribution at every order, okay? And then the 3 Ligand has a contribution also at 3 loops. If now I say I want to generate this one for L equal 4, then there will be other dimension that comes inside here, okay? Now we have seen how the various contribution, which are the monomials that enter from this algorithm, okay? So and then we just have to fix A, B, C, and D, which are the coefficients. Here I have already then fixed them, And this is what we're going to do tomorrow. We're going to compute them and compute them using a variety of techniques, because these are universal coefficients that can be computed maybe with arguments which are not even in field theory. But you know that these are the only coefficients. And for example, for the Ising universality class, you have only the 1/2 and the -1/2. These are the only two numbers. Then these two numbers will conspire when we compute the beta function to give you the -17/3 of the two-loop contribution. But everything in the Ising universality class and in the Epsilon-Expansion is a combination of these three numbers, which is the universal data. So we have managed to set out really the kernel, the only valuable information in the Epsilon-Expansion from which all the other information is built up. So there are only three computations to be done in Ising in the critical 4, and this is actually remain true for any n. So you want to study a theory with the symmetries of, I don't know, some particular group O2 times O3 times O4. There is no new computation you need to do, because this table already has all the information from the RG, because there is only one way to promote this thing to have indices, and the coefficient will remain the same. So these three numbers so these two numbers and the one in the other table are the only relevant numbers of the critical 4. All the consequence, and also the existence of fixed point and so on, which is related to these components, and the structure of the symmetry that I decide is already encoded in this table. So this is really the summary of what is universality in the Epsilon-Expansion in the one component case. What is important really is that in our top-down approach is first we find out which are the upper critical dimensions. Then we realize at which loop order I can find something. Then I construct the vertex set by the topological rules, which is simpler than enumerating the diagram. And then we complete them in such a way that they are dimensionless.
You still haven't told us how to compute the numbers.
Yes, this is the point that we're going to do next time, tomorrow. Tomorrow we're going to have a combination of ways to compute the numbers. And also just remember that only the first two numbers are universal, scheme independent, because starting from free loop, for example, different scheme will lead to different numbers. Okay, this is another important thing. So basically, we have one table like this for the potential, and then we have another table for the anomalous dimension function, okay, which is this one.
Sorry, can you explain? I'm not understanding.
So this is the beta zeta.
No, that's fine. Can you go back to the previous slide? So you said that only the first two loops is universal.
No, the leading order and next to leading. For Ising is first two loops, but for tricritical is like this one and this one.
Okay.
For the tricritical Young, this is universal, and also something at 6 loops is universal, and so on. Okay, this is the ski. This is the table for beta V, and this is the table for beta zeta. Okay. So having this means that we have all the RG information for a given theory. Okay. And now what we need to do is to find the most convenient way to make the computation.
And there's a way to get like transcendental pieces out of.
Yeah, transcendental pieces come down. So these are three loops terms. They have transcendental. This is actually for this one I don't have any trick, but for other ones you can have some tricks to get them for the relevant ones. Because it's only the first two to be scheme independent, so that they will be independent of any scheme. So for example, if you use a massive scheme and then you expand and look for the dimensionless terms, then it will be this one.
I don't understand why only the two first ones.
Yeah, we will see this in 2 lectures. You know, so one argument I can give you, there are two, is that when you compute the beta functions of the marginal couplings, you can show that any reparametrization of the coupling will leave the leading order and the next to leading order invariant. Okay. This is a standard. This is how it's normally done in the Weinberg textbook in many. Now, I can just choose here to put myself in a situation where I have only the marginal coupling. And so these coefficients here are in 1-to-1 with the coefficient of the beta function of the marginal coupling. So from that argument, I know that they are scheme independent. Okay? We can also do a more general various ways, but at the end, the conclusion is always that one, that in perturbation theory, only the first two orders, they are scheme independent. Okay, I'm gonna stop here for today on these tables. So tomorrow we are gonna compute the numbers and fill it out. And then the day after we are gonna do the RG analysis starting from here, so that we see how for each one of these theories, these things explodes in all the beta function, in all the critical exponent, in all the OPE coefficient. And so everything which can be computed and it's universal in the Epsilon-Expansion comes out from these numbers. So what I wanted to convey with this reformulation, first I wanted to have a synthetic picture of universality classes in the upper critical dimension. This goes together with the picture we drew before. So this is the upper part of where, if universality classes exist, you know, their upper dimension is this one, and around this upper dimension, the critical quantities can be deduced in this way. And so, and up to now, we do not know almost any example in the normal conformal field theories, which are conformal field theories, which do not have something in the upper critical dimension from which they originate, let's say. And after we have done this, we will realize that this table basically, most of this table gets promoted to the multi-component case without any additional computation. So it means that we are really focusing on, okay, let's see which are the symmetries. So decide the symmetry, obtain the beta function and the flow, or even in the last day, we'll just classify, for example, with 2 components or 3 components, all the possible universality classes. So because here we have we have access also to the most general set of beta function without any symmetry imposed. So we will really see that the RG will give us the emergent symmetry of the fixed points. Normally when we do RG, we say, okay, let's do the ON model, let's compute the beta function. But the ON model lives in a space of couplings where there is no symmetry. And the ON symmetry is only present on a subsurface. So we are now in this functional formalism, since we have all the couplings, we are in the possibility of relaxing the symmetry and seeing symmetry emerge as a property of the fixed point. And so we really see how fluctuations generate symmetry. Clearly, in the context that we are working only around upper critical dimension. So this is all in the Epsilon-Expansion. But this is a first draft, a first map of what universality classes you can expect. So then, since we're interested in integer dimension, you expect in any dimension that the universality classes, the CFT that can exist, should be some of this table. Maybe not of all of them, because when you have multi-component, for example, you can have that some universality class becomes first order. But in any case, it's in any case the sign of a transition. Okay? And so this is the general, it's a tentative approach to attack the problem of universality in full generality. Let's try to enumerate all of them. And then we will see that since we factor away the RG part, we will focus on the symmetry part. For example, we are going to do what we call Platonic field theories. So all the field theories that have symmetries of objects in 3D. So you know that we have the ON model, which is the maximum symmetry. Then we have cubic models that have the symmetry of hypercube. And then we have the Potts model, which normally have the symmetry of the simplex. And so the cubic and the simplex have representation for any n. But then with 4 components and 3 components, there are, in 3 components we have the icosahedral symmetry, and which is new just to the 3. So we have a specific theory. But can we construct this theory with upper critical dimension 4? It's a group theory question, because we need to see if the icosahedral symmetry with the 3-dimensional representation can host invariance of a certain power of the field. If not, it means that we have to choose another upper critical dimension. The first one, and we will see, for example, that icosahedral symmetry can host only, starts from the 3 critical, because the smallest invariant that can distinguish icosahedral symmetry from spherical symmetry has 6 fields. So it means that there is no icosahedral fixed point in 3 dimensions. But the icosahedral symmetry can be represented as a rational conformal field theory in 2. So you can really start charting out. So you have a problem with a specific symmetry, or you have a specific group, or we're even at the point where, given a group, we construct the field theory. So you enumerate all the groups, you have all the field theories, and so you somehow you complete this chart. So to do that, we took this more abstract approach. Because if every time you focus just on the coupling, then you will, every time you compute the beta functions, you don't realize that when you go to more components, you don't have to do all that, and you factor out the problem. So this is, let's say, the goal of this little course. Okay. That's it for today.